Thank you everyone for joining. I know everyone's very excited about this session, as am I. Shinya is going to be talking about creating an LLM from scratch. So take it away, Shinya.
Okay. Thank you, Shakar. So hi, I'm Shinya, staff backend engineer in DuoChat group. Today I'm going to run this session. Let's build LLM from scratch. So the goal is to get the mental model of how LLM Duo features are working, including the LLM part that is a black box. I think most of us in this call are involved with some Duo features, like a Duo chat, and then like using Anthropic API or open source models, Vertex API. But maybe like you have no idea like what's happening in this LLM thingy. So that's that's what we're gonna learn today. And we build a bigram language model, which is kind of hello world in LLM world. This is enough to understand how the LLM works in general. In a model LLM is use transformer networks like GPT, Claude, Gemini, Apple models. These all use, and also open source models. Like whatever it is, when it comes to LLM, they use transformer networks. This is kind of like specific type of deep learning network. We will cover this in the next session. So consider this is like a part one. Like to step up to the transformer networks, we need to understand some like fundamental stuff. So yeah, feel free to ask questions anytime. We also take time for QA later, and then probably approximately like 1 hour session. It might pass a bit depending on the progress. So without further ado, let's get started. So now we are in this Google Colab. Then first thing we're gonna do is let's write a pseudocode. So usually LLM app goes like there's a prompt, GitLab DOS, and then there's a model, and then we pass some prompt here, and then response. We get response, and then if we print out the response, then like we see something like a GitLab DOS AI assistant or DevSecOps platform or something like that. So GitLab DOS the what we passed, and then the rest are completed by LLM. And then I think most of you are interested in chat model. It has bit more structured inputs like role and user and the message and hi, how are you? And there's a system prompt to tell that you are helpful AI assistant or something like that. But we are going to cover this later. At first, we're going to finish this completion model. So the first thing is that this doesn't work because this model doesn't understand text. Like we are having this text, right? Model doesn't understand string. So here's a picture what model looks like. So there are bunch of dots here. This go to neurons, and then like neurons are connected to each other, and then this is the first layer and the second layer. The intermediate layers called the hidden layers, and then we get the something like output, the final layer, to get some like meaningful data. And the important thing is that these neurons don't understand string, only numerical values like integer or float values. So first thing we're going to do is to convert this string into integers. So transformers. I'm going to install library. Transformers. Control runs for Mars. Okay, got it. So well, install link. Let's give you let me give you like how it works. Wait, with the GPT-2. So I just install and then transformers, and we're going to use Tokenizer. Tokenizer is a tool to convert the string into token IDs, the integers. And then let's say if we pass the GitLab DOS, this is a tick tokenizer. This is a tokenizer for GPT models. I'm currently choosing a GPT-2. And then if I pass GitLab DOS, then it's split in this way. For example, G is 38, ID 38, IT is 270, and then and so on. This ID, this ID. So tokenizer splits into chunks, the smaller thingy, and then like assign the value, the ID to each piece. And then like imagine like you are seeing an index page of an English dictionary. Like let's say Apple is page number 1, banana is page number 2, something like that. So this tokenizer has this mapping. So if I type G is 38, and if I type GG, then it converts to 11190, not that 38, but it's compressed into one token because there's a definition in this dictionary. And if we GGG, then like it's split into 2 again, like we get the 38 again, because like there's no definition of GGG here. So that's how tokenizer works. And then
and do the LLMs publish this? Do they publish this, or is it you get this through an API? This tick tokenizer gets it through an API, or do they publish their tokens?
I think this is run by a community, not the OpenAI. But the tokenizer itself, we're gonna download tokenizer from Hugging Face, and then for example, GPT-2 model is open source, including the network itself. So
I see.
Thanks. Yeah. The tokenizer, and then tokenizer from retrained GPT-2 tokenizer encode, and then we give a prompt, and the return answers is PyTorch. Today we're going to use PyTorch as a deep learning framework. Then here's a token, and I'm going to create this. Let's see token here. We're downloading tokenizer, and then here we get the I think same number. Yeah, this number. We get the same number here. So now we have this token ID representation. So like one step forward to pass this data GitLab DOS to model. And the next thing is actually we start writing a model. Import torch, NN is a neural network. Then I'm gonna Claude, but I'm gonna name our model as a Claude, but Claude is taken by someone else, so I'm gonna do Claude da, and then module. So then imagine that now we have this blank canvas of defining these neurons. Then let me quickly define the layers. Embedding. Then sure. Size. I'm going to explain these details later. Size. Heading. Then go 8. self-linear and linear bidding for your sites forward self embedding x equals x. And done. This is our model. So let me explain what's happening here. So first, like we are passing x is like the data. We are about to pass this, tokenize these tokens, these numbers to model. And the first, this embedding layer is gonna convert that this token ID, each token ID to vectors, something like 0, multi-dimension vectors and so on. And this vectors dimension is, as we defined here, 728. So like imagine we plotting token. This is a good animation how the token is plotted into multi-dimensions space. Like we are placing this token ID into multi-dimension spaces like this. Then each token facing different direction. And then we get the vector of this. And then the next part is that based on the this vector, we get the prediction like token ID, like model goes and predict that maybe the next token comes after GitLab Duo is the 318 token ID 318 after comes after 318. Maybe it comes, I don't know, token ID, something, but token ID, yeah, something. That's how model works. And then in transformer model, I mentioned earlier that like, modern networks, they're all based on transformers. They have consider that like they have a very large networks here. But important thing is that whatever their model looks like, they produce the same thing. Like what's the next token is after this one, like, given that we pass these tokens, this model produced that one token, only one token. So now we have a model, then why not use it? So Plata model. Then model, we get the token here. So we get pass token, then logics. I'm going to explain this later. And then we are currently generating a next token. Softmax logics probability torch multi-nominal probability gen token ID generate call nicer token front it's gen token. So now we are trying to use this model. First, we define a model, and then the model gonna predict that the probability of this. Actually, it's better to see that what's produced at each step. Let me see. Okay, size is defined. Okay. Okay, I forgot super in it. the first logics come in, and then softmax it's dim. Hold on. Yep. Probability, some samples. Okay. So here's what's happening here. The first we define the model, instantize this model, and then we get past the token, and we get the logics. So logics looks like this. Here we have that 5 by, I think 5 by token ID. So 5 by 54257. This is the vocab size. This is like dictionary, like total number of defined words. Like each token is defined has assigned to a dedicated ID. Like A is 0, the B is 1, and there are 50,000 definitions here. And then basically this logic saying that for the token is this one, the last token ID will comes likely 0.5 probability, and then the next token is the negative 0.4, meaning like after the is, most likely ID number 0 comes next rather than ID number 1, because ID number 0 has a higher value, 0.5. You see, like it's bigger than my negative 0.4. And the next one is like a probability. At this moment, it's hard to use this, like positive or negative values. So we convert it to percentage. So we get that, for example, like E negative 0.5 means like a 0.02%. Like the probability of token ID 0 comes next is 0.0002% or something like that. And then we get all the probability. And then we get the torch multinomial is like plucking the one token based on the probability. So generated token ID. So based on our model, it says that, hey, after this GitLab deal is token 318, most likely token ID 4 or 426 comes next. That's our model saying. And then here's a generated token. The GitLab deal is shroud. Or GitLab deal is, what's this? GitLab deal is warm. Something like
why does it change? Isn't the probabilities, shouldn't they always be the same?
No.
Did you add some? Like the first one should be the one. If we pick like no temperature, right? Then it should be always the first one, the one with the highest probability.
Actually, that's a good question. Like when we initialize a model here, these all probabilities are randomly initialized. So like a vector is every time we initialize this model, like all the vectors are totally like randomized again. And then so like every time we see, model gives us a totally different probabilities. Like it doesn't make sense. Like do the selection. So what we're missing here is that training. So like in any models, the way it initialized is like totally randomized, like the vector is facing wrong way. So we train the model that like, the making them like towards specific direction that somehow makes sense to us. And then,
okay, can I say it my words? So basically we now have like we have a model that's not even formed, right? It's just clay, and what we now need to do is we need to form it. So this is why it comes up with random results.
Sorry, I don't get your question.
So the model that we've created is not really modeling anything. It's just random numbers in a huge matrix that then comes up with those, like in this case, is selection, right?
Yes.
And what we now want to do is we need to train this model so that it actually reflects anything real about the world, right?
Exactly.
Okay, I understand. Thanks.
Mhm.
Yeah, because we don't have any model weights at the moment, right? We haven't trained the model, so it's just using some random weights at the moment. I think when you do self.linear there, it's just calculating some random weights and bias or whatever that it had, right? And so I have a feeling that that's why it just gives you any random selection at the moment.
Exactly. So that's also a good point. Like there are weights and biases. Like if we print a model, we can see that like these layers, the first layer is embedding, and then the next one is a linear. In features, these are actually the weights that like influences the output. The we are seeing the largest. Largest is the output, the most important thing for us. And the weights and the biases is gonna be tuned up during the training, and then that gives us a better results. So yeah, the first we're gonna do your wait, it's training. Let's get the training data from GitLab. So since we want to train dual chat model, dual chat knowledge, dual doc dual, GitLab dual. Let's say we use this text for the training as a training data. And then here's a raw text. Then we go into and we get downloading it. And then it's open index ability. Read as file. File read. And then text. Here we loaded the file. Right? Yeah. Here's our training data. And then like we did the same, we need to tokenize first because model doesn't understand the text data. So we're gonna give this text to the tokenizer, and then here's training tokens, and the training tokens gonna be there are actually L2 need one, yeah. And this is a target, so go to 1. Then XY that. So what I just defined here is that training the tokens looks like something like the numbers, the integers of numbers, and then I split into two. Like X is a target. So X is the input, and Y is a target. So the training looks like this. The target data is drifted by one index, something like that. So when we plug that first training data, then like we get the 394, and then the target data is this token ID, because like base our model in background language model, we want to predict the next token based on the previous word. So like when this token comes, like this token should come next, and then this token should come next based on this one. So like we prepared a drifted data set for the combinance. So like when we plug the index 0 of the these arrays, then like we get the compare these things. Like when we pass the 394, the model predicts something in a random number, maybe something more, let's say like some number, and then like we tell to model that, hey, you should produce this ID. So like a model can calculate the loss. We're gonna visit later. So that's what we're gonna do, and then let's define the model again. The model. Then step training number for I in range step and model. We need a pointer. Then x equal training equal x pointer 2 pointer plus chunk size it's 100. Training y is y pointer chunk size pointer increment chunk size pointer what's that links training tokens. Okay, let me finish this code first. Training, then loss, sorry, logits and logits, gorge and functional plus entropy control low P logits and then training y and then loss. Okay, let's take a break at here first. Let's hit run. Seems it can run. Okay, so like we did the x, y, and then initialize a model, and then step num is like a number of the training. Like this is like only we train once, and the chunk size is that like we get the batch of chunks. So here's our training, training text. At first we get the first 100 chunk, and the next to get the to get the new data per iteration. And then every iteration we get the new data, new chunks, and then like we pass these chunks into model, and then we model the prediction. And then the interesting part is that toward channel functional cross entropy, there's a calculated cross entropy loss. Like it basically like gives you an idea that like how the model prediction is off from that ground truth. So like we did that like when we pass that 394, then like model predicts something in the token ID, but it's pretty off from this ground truth. So like 10.9 means like pretty high. At this moment, this is actually like from the untrained model perspective, the chance that it can predict the next correct token is 5257. So 1 out of that total vocabulary size token ID, because this model isn't trained at all. which gives us like kind of same number, 10.82. Yeah, see, 10.92. So that's a kind of like a beginning of that training process. And then we gonna define optimizer towards optim the model parameters is it correct? Then optimizer reset the gradient, and then here's a interesting part, backward. This is the backward propagation, and then optimizer step. Okay, does this still work? Let's increase that training number. Okay, first, last. Yeah, we successfully finished the 5 iterations. So this this is the backward propagation. You can see that more details about the back propagation, how it works in this this Blue While Brown. He explains excellently in this YouTube channels. But basically, like the basic idea is that it feedback this loss, like how off from the ground truth to the model. So like neurons are, that like Sharker said, weights and biases are tuned based on this loss, so that the model can gain the accuracy towards that, what we want, based on this like a training text. Then at this moment, we want to increase that step num to something like 1,000, but still it's pretty slow. So we're going to switch to GPU model. Then just switch to GPU model. What we're going to do is torch CUDA. So first, we're currently using CPU. If torch CUDA is available, then we switch to CUDA device. CUDA is like a GPU, it's being said that like it's pretty, known fact that whenever you use models, you should use a GPU, and you will see that how it's going to speed up things. So I'm going to put the model on CUDA, and also I'm going to put this tensors into CUDA to device. So hopefully it works. Okay. I restarted the session, so like I'm running from top to bottom. See, yeah, it's much faster. This is the power of GPU. But what we're gonna do is actually not plot live display loss. We want to get the nice visual. So we use matplotlib live here. Okay. Loss values. Loss. Please append loss. CPU touch NumPy. And let's see. We are training 1,000 times and then like iterating through that the text. And we are slowly seeing that, like, numbers going all the way down to 1 or 2, which is like the accuracy, the model predictions, the accuracy is improving.
See, this model is only predicting one token, correct? Or is it predicting more than one token?
It's the bigram language model, so like it's basically like one token. It gives it one token and it predicts the next token. Then here's how our model is smart. It became smarter per iteration. So like the first we started from around 11 and all the way down to around like 100 iterations. Like it started reaching this like this wall, hitting the wall, that it doesn't go forward. That most likely because like our model is pretty small. Like if it's big model like transform models, it has more capabilities to learn the things, so like it will go way down, or maybe it doesn't have any like bumps like this. But here is what we have today. And then why not use this model to generate the stuff again? So our model was like it's a bit didn't really make sense at first, but let's see. We torch no glad. We're gonna tell that in this time we don't train this model and then token logics. This doesn't need probability. Generate token. This doesn't need. Then let's say max token sequence. Max token num. Let's generate 10 tokens. 10. Then the first get the logics, so then logics the probability, then generate token ID, then token ID, then gen text, and gen total text. Total text is like this, and then here is our input, and then one thing we need to change here is that because like we want to predict the next token after what we got the predicted. So like our what is our token? This one. Here's our prompt here, and then here's our prompt tokens here, and then the first generated token is predicted based on this is, like after is model predicts the next token, and then like something comes after, and then after that we want to predict based on this generated token. So we're gonna do is that torch concatenation token generated ID. Oops. Generated ID, then append it. How about now? It doesn't work. Why is it exhibit all the tensors on the device? So I token to, let's put it to do that. GitLab Duo is area art guard. Question, what does it mean? Okay. So here is that it seems pretty off still. And why is that? Is
it only predicting based on the last token? So it's only predicting based on is? Because is like a super common word, so it may be really throwing off. If it's only predicting from the like last bit, maybe leaving us there like just GitLab Duo without this may help it with like limited model you have.
Yeah, like the last time I tested it, it's pretty much more. Oh yeah, like something like this. You know, at first like it didn't really make sense, like pretty gibberish here. But like we're slowly seeing that, you know, like these generated tokens are facing towards that like specific direction here. That like if you know we are seeing that more GitLab, like GitLab deal is our limited time. See the status of the teams that are also available in GitLab dedicated GitLab, like root cause analysis, GitLab deal chat, view documentation, then something like that, GitLab Duo Pro or enterprise outcomes. You know, like it doesn't make sense, but like you know, kind of like trying to tell that like some words and text here. Sorry, did I answer your question? Sorry, maybe I didn't really answer question, but
He's not,
yeah.
Mikola, you're not taking just one token to predict, right? So he's taking that chunk size and then you're predicting the next token after the chunk size, right? And so you're taking like the first few words in the chunk size and you're predicting the last token from the chunk size. So let's say they were like, let's say the chunk size is 10 and let's say it's 10 words. And then you're predicting the 11th word after taking those 10 words. I'm not saying the chunk size is like, is in characters, but still.
So it
Yeah,
takes
so
all the tokens at like all the tokens or like some vector size. So the vector size of the input tokens that is used to predict is larger than the one. Is that correct?
Yeah, so if you go back to the training code, Shinya, so above you have that training code, right? So he's taking the training data from that pointer to pointer chunk size, right? So he's taking from, let's say, 0 to the chunk size, which is 100 in this case, so 100 characters. It's giving and it's asking to predict the next token in after the 100 size, right? So 101 token it is trying to predict. I think that's what's happening.
yeah, so like the training phase is that like you know, we are seeing that this is a token, and then like these are split into token IDs, and then you know, basically like this bigram language model is a predicts the next token based on the previous one, and then like what's happening here is that like something like this, they're passing the 100 chunks here, and then the comparing this loss, like half off from the each you know target value is an input, and then here's a target value. So that's like a you know each token is gonna learn that what comes next. The bigram language, the bi means like there are two pair, the one pair of that the you know two tokens. So like we give one token and one get the one prediction. And then the generation phase, like what we are doing here is that the GitLab Duo is that's like our prompt here, right? And then like it is when we pass is, then like model predicts the next token and then when we model sees and then it predicts the next token limited, and then like and so on. When model sees a limited, then limited model predicts that it's time, and so on. That's like a binomial language model. If it's transformer model though, like a you know large language model, the actual large language model, then like its references total whole previous tokens. So like imagine that our model is token window, context window is one, always one. Like when love is passed, it's a duo is a duo the next is. But the transform model is like use whole 10 tokens to predict the next C, and then the next generation use the whole 11 tokens to predict the next and so on. So that's like a kind of difference here.
It's very surprising that we still get like is a limited time. I mean, this is exactly in the documentation. So when it's really only considering is, then you could swap GitLab Duo, for instance, to root cause analysis is, and it would give the same limited time.
Cause analysis is, let's see. No, root cause analysis is details. I don't know what like are these tags appearing in our doc maybe? It looks like a tier offering tier GitLab Duo Pro or Ultimate. It looks like a something appearing in our doc.
But we have not retrained, so it's still the same model.
Yes.
And we haven't given it any like randomness to. So why is it not exactly the same as if we have Duo Chat is? If only the token is used to predict the next one.
That's very good question. So that's like the point of multinomial. Like that's our expectation, right? So like whenever is comes, like that always same tokens should come next. But the reality isn't that one. Here's how probability distribution looks like. Like when imagine that at the logits, we get the prediction, and here's a softmax the prediction, and then we see that 550,000 of token IDs, we get the whole probabilities for each token, something like this. Dumbledore is 0.01 like 1%, and the Snape is like 60%. And then like when we pick the token, like when we pick the token, we think that we should get this highest probability here. Like we should always get the Snape here. That is called argmax, torch argmax. That's a different way to pick up the token based on probability. But given that, like, that is not the right way to use the probabilities, because like, yeah, sure, like this token has the highest probability. That doesn't mean that there's always comes the next, because like it's 60% of a chance. So multinomial means that like still we pick a token based on this probability. So like, lower probability tokens still has a chance to be picked up. Like, these are the tokens, like a Dumbledore still has a 1% to be picked up here. So that's the reason, like, we're seeing different, generated result every time. Does it make sense?
So it does add some randomness if you go back to the Dumbledore example. So you have a higher probability to pick Snape, but you're adding some randomness to also pick something else.
Not really random. Not really randomness. Like for example, like Snape comes 60%. That this token comes at 60%, and then like that doesn't mean like Snape will differently come. Like it's not 100%.
Okay, I understand.
Right? Like if it's Snape is 100% and the other token is 0%, then like we should always get the same thing. Like when the is the next is like this square bracket, then it always comes like this square bracket token is 100%. But it isn't. Like tokens are basically like a still has probabilities like even like highest like 60%. Yeah, so that means like still has a chance that it doesn't pick the highest probability.
So to just maybe rephrase to make sure that so I'm getting it. So the way or the algorithm that I'm using to select the tokens based on the probabilities that the model generates. So model generates as the set of these probabilities. So like this chart. Model generates this chart for the next probable tokens. And this multinomial is basically making a kind of a lottery, like selecting the next token from this probability. So it's kind of making a lottery, and it has
Yes,
the
exactly.
60% of a chance of selecting the Snape, but there's 1% of it selecting this lottery a Dumbledore.
Exactly. So like imagine like whenever we generate something with the LLM, we always roll the dice.
Cool,
That's why
thanks.
that's why some they try to set the seed, right? So that the randomness is reduced because it's picking them randomly. If you set the random seed, then it always picks hopefully the same one each time, right? And so like you can reduce that randomness if you wanted to, I think. But back to like Mikolai's point around it is only trained on one it's only trained on one token to predict the next token. So if you remove is, because is probably a token and there are probably many is there. Like so if you just say root cause and then you try to predict, does it give you analysis? Like because the chance that cause is next to other things is smaller, right? So
that's
it,
good. That's good point. Yeah, analysis. Root
yeah.
cause analysis next time. Root cause analysis. Wow, yeah. You're correct. When we pass the root cause, it almost 100%. So far 100% chance. Yeah, it gives us analysis.
Yeah, that makes sense.
In the there is this like idea in the natural language processing that we're removing these super common words when we're analyzing the text because they basically add no value and create this kind of mess. So like this all kind of is there are removed from the set of tokens very commonly when we are like dealing with the text analysis.
Also in the language model, in the LLMs, when you have the attention layers, I think in the attention layers, it decides what to focus on, right? And so which words really need to count towards the final probability, like it decides the weightage. And so I think that's like a main difference between the modern LLMs is that those attention layers determine what should happen next more. And so it won't focus on these like filler type words like is a, and instead we'll try to understand what, which words it should focus on.
Yes. So like the attention layer, this topic we would cover next in the future. That's one of the key concept of the transformer models. The self-attention, like basically tokens is gonna talking each other, and then yeah, also like the multi-layer perceptron that is like a kind of encoding the knowledge into the transformer, this deep learning network. That's something like we'll cover next.
Yeah, I have a question. So could you
Sure.
replace this multinomial one with this argument max?
Okay.
Will it then just rewrite the text that we have put in? Is that a way how I can recover, for instance, the source data of a model?
So I don't get. Wait. Argument zero dimension. Zero dimensional tensor. Gene token ID. I think should be Forge tensor. How about now? Expected. 1 sec. Sorry, it's very dirty code. How about now? Yeah, here's the result. Root cause analysis We're going to cover this later, but
Mm.
actually this is
That's
related
interesting.
to temperature. We're going to talk about this shortly.
Mm.
That like repeating, it's kind of unnatural way. Like these tokens are making sense for us. Like .com self-managed. That's what the word we want. But like it doesn't like a sentence at all. So yeah, we're gonna uncover this later. Okay, so well, it's like we're running out of time, so like I'm gonna move forward. It's okay, and then the fun part starts from here. The next thing is like, let's replicate Anthropic V1 messages API. This is actually what I really want to do. So here's we are saying create a message API. This is what we are using to build a dual chat. So we're using a Claude 3.5 or something. The Sonnet. So yeah, basically, if we pass some messages prompts here, then like we get some response from the Claude. Then I'm gonna try to replicate some of the like how this API works in this code, so that we can get a better idea what's happening under the hood. So the first parameter is a model. This is just like selecting a model. So imagine that we have this one model. So like imagine we have multiple classes, and then we just switch based on this model. And the next one is messages, input messages. So this is the first thing I told you, that maybe you're more interested in chat models than the prompt, the completion model. Like currently we are doing one text sequence, but actually like this messages API look like a role and a message. And then the hint is actually in the tokenizer. I'm going to switch to GPT-4. GPT-4. So here's a GPT-4 tokenizer. We already seen that structured messages. And then the first message is the system. Anthropic also has a system. It's actually a different field. And then messages is like role is user, and then content is hello Claude, and add it. And then please pay attention to this one. So this structured message, like something like this, is actually flattened into one string like this. So I am start system, I am separate, and then there's a message, you are helpful assistant, I am end, and I'm gonna new line here. I am start user, I am separate, hello Claude, I am end, I am start assistant. So basically, this structured message in a chat model is separated by this special token. This is like a we can define in the tokenizer. We are currently using GPT-2 tokenizer, which doesn't support it, but some of the tokenizers support special tokens to separate to represent this structured context. So like always, the first message starts from I am start special token. The role comes next. And then I am separator indicates that message about to start, and the message comes next. And then I am end. That's the end of the message. This is a system message. And then the same thing goes to user, then separator, and the message comes next, hello Claude, and then I am end. This is the end of the message. And then I am start, and then role, assistant role, and I am separator. And then message comes next. So that like, it's kind of same with what we're doing. Like it's just like if we flatten out, this is like what gonna happen after we pass the structured output to the Anthropic. And then like these special tokens are assigned to special token IDs. Like we are seeing that IAM start has a 200-264. That means like this isn't conflicted. This isn't conflicted against anything. This is very unique, and this token is used to train chat model. So like we use this token. We use Tekis, this GitLab doc for the training, but chat model training data looks like this. IAM system, like they Anthropic or OpenAI, whatever it is, they prepare tons of this type of training data to to accomplish the human like chat style completion, and then like they prepare the this type of the training data, and then like most likely hello Cloud, Cloud, how are you? And something like, there's a ground truth is also filled here. So that like we feed this as a training data, and the model predicts the next token, which is I. We expect I, but model could be, model could produce totally different things. So like we calculate loss and the backward propagation and the next token, and so on. So that's like a, at a glance, chat model looks totally different, but deep down, it looks pretty similar with what we did, like completion model. It's just like the how structured message is tokenized, like flattened and tokenized. So in that sense, like I consider that like we already covered the fundamental part. It's it's just about how the training data looks like, and then special token is defined. So I'm going to skip this. And then the max tokens, we did that. Max token num, so done. Metadata, this is unrelated. Stop sequences, custom-text sequence that will cause the model to stop generating. This is actually pretty easy to implement. Stop sequence, let's say GitLab. We are seeing some GitLab occurrences during the generation. And then let's stop that generation when GitLab appears. So for stop sequence and stop sequences, if stop sequence in generated text, then stop sequence hit is false, stop sequence is true, then if then break. See, now our generation stopped at this specific token. It's that's it. Like it's pretty fundamental part. I mean, like it's pretty simple. And the stream is like interesting. Pretty straightforward too. So stream is, let's say stream is true. Streaming is like streaming chunks to clients instead of like giving the whole completion data. So if stream is true, then we just since I don't have a HTTP server here, so I just want to print it. Respond chunk to client, then here. And then if stream is false, then we print at once. So here, I'm gonna turn off stop sequences. See, like it looks like the first we're streaming the data, the analysis. Seems weird. This is because a new line. So each chunk is why it's appended, because that's not what we want. Okay, it looks like that. So each token is streamed back to the client. So like analysis and managed sees the latest GitLab dedicated answer pick and something like that. If you have experience that to debug Duo chat, maybe you saw something similar. Then if it sets false, then we get the ones. So we cover stream, and we also covered system in this one, right? Then temperature. So temperature, we're running out of time, so like we quickly squeeze it. Temperature is about, actually, this is a better explanation of temperature, how temperature works. So we get some prediction, right? In the next one, sorry, temperature. Like temperature is like a flavor to control the predictions. So first, like we get the Dumbledore and Snape case. Like Snape has a 60%, but there is a like a parameter, optional parameter to squeeze this, like lower the Snape to 30 and upper the Dumbledore to 30, so that like more randomized. And the temperature zone means like influence that highest probability to 100%. That's what we exactly did in argmax. Like Torsten sort of said, like what's going to happen if we use argmax? That means like temperature zero in this case, like fully ignore all of the lower probability stuff. And then this is actually pretty straightforward to do this. Actually, this is pretty far from the accurate thingy, but I think you get an idea. The temperature, we manipulate the logits, multiply logits by temperature. 1.0 means like no affection. Then like we try to 0.00001. Then like we squeeze the probability, like compress it. So like all tokens have totally randomized. Then like we see that like root cause 009 much responsibly grows rare poems, completely random. But how about we set the large value? Then like root cause analysis, manage GitLab.com, self-managed, GitLab.com, self-managed. Isn't it like what we saw with the argmax? That's like because like highest probability token is influencing this generation and ignoring that the whole lower probability stuff. So like actually like temperature should be need to be tuned to the like reasonable value, not too high, not too low, so that like we can get the more natural human style language, and something like this. And then the last part, we only have 10 minutes, so this is the tool is the last one. Top K and the top P's are actually, yeah, we should use temperature instead. So the tool is so tool is a definition of tools that a model may use. So this is in other words, this is a function call that like we can pass these tools to the model so that models can pick a tool. Like each tool definition includes name, description, input schema. Name is this one, and like it gets stock price, and then like this function does this one, and then this is an interface of function, and the model decided that we gotta use the tool, then like it returns this tool name so that we can execute this tool and then like back and forth to get the better result. And then actually like does anyone have an idea how tools are passed to the model? The hint is actually in the recent Anthropic cache doc. Prompt caching better. Not the largest tools. So here's an important clue here. Prompt caching caches a full prefix. So let me explain how prompt caching works. Prompt caching references the entire prompt tool system and the messages in that order after including the block designated with cache control. And then here is like, we request to B1 message to the API and specify system prompt, and the system prompt you are AI assistant. And the next one is like we specify cache control. So like something is cached, but what is cached? That's important stuff. And then we come back to this tokenizer, and then we are, user, hi, how are you? How are you? And then these structured prompts are flattened as one string and then converted into tokens. And then, like Shurker said, in transformer models has a self-attention and the MLP to look up that has a larger context window to look up what's like basically tokens are talking each other. So like it can understand the contextual stuff. So the first token is processed, and then the next token is talking each other, and then like next token talking each other, and updating that self-attention has to calculate the QKB. We're gonna visit this in the next session in the future. But basically like it, in short, it's basically like processing token one by one to update the model internal state, to one by one incrementally update that what kind of context is being asked in this prompt, what is like related stuff, and then this is like a simply put ON. The process 1 token, 2 tokens, 3 tokens, 4 tokens, and then like it repeats until the end. After we reach that the prompts, model generates the next token, and the next we do the same thing, like whole tokens, the next generate next token, and then the whole token, next token. And then so like it's really computation wise, it's really inefficient. So that's the idea, is to minimize the computation time, is that to cache the internal state. Let's say like we have a cache control annotation at this, let's say, how are you is like this one, like when the model calculates that internal states at this point, we create a checkpoint. Actually, PyTorch has a PyTorch save and a PyTorch load function to get the loads are first saves the model state and then also loads the model state and at a specific position. So when we saw that exact same token ID sequences, we don't calculate from the beginning, but we load this token state, the model state, and then we start from the next. So like we can skip like, I don't know how many tokens here, but like 20 tokens, 20 iterations can be just O1, becomes O1, one computation, just loading the model state, and then we can continue the generation. So that's the how the model cache works. And then if you're interested, and I recommend going to Hugging Face transformer models, Hugging Face transformer repository. They have many models. These are all transformers. There are, and also many famous ones like a GPT, and then like a CodeGemma, and the Llama 3 too. Gemma 2. And then you can see the actual code here. And then most of them have a cache like this. So that's if you're interested in. And then we kind of get the how cache works. Then let's go back to the tools. This one, the prompt caching references the entire prompt, tools, system, and messages in that order, up to and including the block designated with cache control. So meaning that probably the first token comes before the system prompt, because otherwise, the talk, like any models, any large language models process a token for the beginning, and then we cannot cache. The cache needs to work in this order. So tool 0, and then a name and a description, name something, and a description something. This UI doesn't support the more structured form, so it just put the pseudocode here. But here's our tools prompt comes first, and the system comes next, and the system is something, and then user, a message, it's user assistant. We sometimes put the chat history if it's dual chat, or could be anything. So that's we can what's going to happen in this if we pass something at these tools parameters. And then in Anthropic case, most likely they will parse that produce data to give us this structured information. But at the model perspective, everything is flattened into one text sequence and one this token ID, array of token IDs. So that's deep down, it's same with what we are doing. We at first generated the token IDs based on this prompt. It's how they use special token, how they prepare text training in text. It's that's a different part. But the part that we generate the token IDs as a sequence and then passing it to the model is the same. So that's all.
I suppose for the model to know this is a tool helps it to put the attention on that, right? So
Exactly.
although the tool is not right next to the user question, what is this merge request? It can take every piece of that text from the user and connect it with the attention to the tools at the top, right? So because it knows those are tools.
So yeah, most likely Anthropic tools, this, the reason why they separated these tools, system, and then the messages, this could be just one parameters, but why they split it, that could be they have a different special token and a different, not using that same special token to separate these things, but say I have a special tool something, and then with the training data, so that it can understand better than just natural language processing, if that makes sense. I think that's all. Thank you for watching. Give it back to you, Shakar.
Yeah, thank you so much, Shinya. This is such an enlightening session, and thank you for live coding as well. That was super risky, but it paid off. It was awesome. Any questions before we stop the call?
I have one around the caching. I don't know if you have enough time. You also answered asking, but as we see, like with this, the token selection based on the probability, like this random lottery roll dice when we have these probabilities. So wouldn't the caching like kinda imprint the one particular output? Because if we retrieve, like we see some sequence of tokens and we have some set of probability, wouldn't this kind of affect it? Like it would kind of imprint what would be the outcome of the lottery each time?
You mean like how the tokens are affecting to prediction?
I mean the caching. So with the cached prompt, if we like always get the set of the probabilities for the tokens like the same, wouldn't this impact the like imprint the result that we get out of it? Or probably I'm missing
So
something.
the caching is actually doesn't affect the quality of the prompt, the generated response at all. That's like by design. Like the point of the caching is just reduce the computation times. This is also documented in the Anthropic cache documentation that the 2 points of using cache. One is like you can get the faster response because like less computation, and the second point is that you get the cheaper price per token because less computation in their side. So like good in their side and win-win. Good our side will win. So actually, to understand this how caching works, we need to step into transformer model. That's like it's tightly related. But I can leave a link in this Google Doc for further reading.
Thanks.
All right, if there's nothing else, we'll stop the recording here. Thank you so much, everybody, for joining, and thank you, Shinya, for a great session again.
Thank you, Shakar. Thank you, everyone.